So, okay, so the proto definition of a generalized manifold is based on this model space idea of, and so my idea there is you start off with every point of the graph has its own UUID.
Mm-hmm.
And you form those UUIDs as digit sequences.
Okay.
And those digit sequences are naturally live on a tree.
Mm-hmm.
And the tree is exponential dimensional, so to speak. Okay?
Yep.
But then the way you make a model space is by modding out some of those tree leaves by some rule. Okay?
Mm-hmm.
And the immediate thought is to use group to think of the elements, but I don't think it's the only way to do it, to think of the elements of think of the elements of the of those ID words as group elements.
Mm-hmm.
Okay.
Right. Yep.
So I mean, okay. So you start from an ID for every point, and that ID, and the ID is a digit sequence or a sequence of symbols. And by the way, that sequence of symbols could be, e.g., the sequence of rule IDs that produce that node. I'm not sure if that's unique, but it could be something like that, if that makes sense, right?
Right, right.
So it's
but this is what we were talking about the other day, right? About modeling out by some non-abelian group and seeing whether there's a connection with non-commutative geometry and
exactly
C-star algebras.
But I don't think it's quite right, because I think there's a more general way to think about this. So one possibility is, so now need to identify lots of ID sequences. Okay, in a uniform way. What does that mean? What does uniformity mean in this case? God, I have to go do something in 10 minutes. Shoot. Okay, in any case, what does it mean to be uniform with respect to this tree?
Right. Yeah, I don't know. My concern is, what is the constraint on dimensionality varying within connected components of the resultant generalized manifold? Because there's presumably some kind of smoothness requirement, but I'm not entirely sure what that means in the context of a model space.
Well, the whole point of a model space is it's only locally agrees with the model space, right? It's only that's the whole point. It's only in this limit. It's like a tangent space, right? It's only in the limit
right.
that it agrees. But so the question is, to make a model space, we want uniformity.
Right.
Is how do we achieve uniformity? What does uniformity mean? So a tree, in what sense is a tree uniform? Right. So if we have,
in the context of something like the beta lattice, right, you have uniformity in a degree sequence, degree of each vertex.
Let's walk through that for a second. Okay. So let's say we have a K-ary tree. Okay. Is this a beta lattice?
I guess so. Yeah.
Right. So okay. So each one of these could as well be, we claim,
the root.
The root.
Yep.
That's
node, uniformity of the kind.
Yeah. Every node could be the root. But now, what does that mean in terms of the IDs of those nodes? Right. I think what it means is, given the ID, one can split. So the ID is a bunch of zeros and ones, depending on which way it went. I'm thinking that what one can do is to, in an infinite such lattice, given the ID, which is an infinite sequence of zeros and ones, split it anywhere and start and consider it representing up or down on the tree.
Right. Yeah, effectively what it means is, you know, you can chop off as many digits as you like on the left, and the thing will still look the same.
Well, the same with respect to its descendants, but its ancestors, you will be...
You're removing them.
You're removing the ancestors, right?
Yep.
Okay, so now, what is the general... So we've given this infinite sequence. We now want to ask the question, what are the natural identifications of something? So in a sense, what does it mean? There's uniformity. Yeah, I think what it means is you can get to, on a tree, right? On a tree, you can, i.e. free group, you can get to a new element by appending any generator, any generators. Okay, so it does really suggest there's a group theoretic aspect to this. Mm-hmm. But I think the full group axioms, including inversion, including inverses, mm-hmm. Why are those needed? I think they are needed here, because I think otherwise you can't get, and they may be needed to go the other way.
Right. Right. I really do think there is a correspondence with universal covering spaces for Riemannian manifolds here.
Well, since I don't know what those are properly.
I mean, in the case of the beta lattice for a free group, it's a direct correspondence. That is actually the universal covering. The map from the beta lattice is the universal covering map.
Covering map is a continuous function from a topological space so that each point has an open neighborhood evenly covered by the image. Yeah, that does seem very relevant, doesn't it?
Yeah, well, I think in the continuum limit, that's exactly what you get, right? The model space is the universal covering space.
Okay, so the universal covering space requires evenly covered. What does that mean? What does it mean, evenly covered? Right, I mean, that is what we want, is something which evenly covers.
Right.
So double cover of real projective space, yes, yes, yes. The diamond crystal as an abstract graph is the maximum covering graph of the dipole graph. Quotient of S3, the quotient space divided by that Z action. P is a local isometry, okay. Yeah, it does seem highly relevant. So in a sense, what you're claiming is that what I'm talking about as a model space is the local universal covering space of the graph.
Yes, precisely. And so in the beta lattice case, that's provable.
What is it? What is the universal covering space?
So the map from the beta lattice to the associated Cayley graph is the universal cover of that Cayley graph.
That's trivial. I mean, it's a Cayley graph for a free group.
Yeah, well, actually, it's yeah. In the Cayley graph for a free group, that's right. Yeah, that's how you get the beta lattice.
Indeed. So my question is,
there's a more general case here, right? That if you have any presentation of a group by n generators, then there's a surjective map from the free group to that group.
indeed.
And I think that in general is a universal cover.
Big whoopee-doo. I mean, that's basically saying that every group element can be, is universally covered in this sense by the free group.
Right.
But the issue here is more, can one classify the set of, can one classify things? So for example, could one get a Sierpinski? Does a Sierpinski arise as a Cayley graph of some infinite group?
Right.
I think it must do.
Right, yeah.
Anyway, I've got to go to my other thing. When are you going to be around later? Well, look, this multi-way system ID thing, you're almost ready to put that in?
No, that's in for states.
But you
and
said
events.
It might break other things.
No, that's repaired now. So
you mean it works?
Well, yeah. I mean, the only issue is, as I mentioned before, without refactoring of the way that we do things like the causal graph, the options for that won't propagate down.
Options for what?
For incorporating event numbers and things. I haven't yet added in a function that will figure out when it's okay to strip out. I mean, look, the problem is our operations on events that we need for the causal graph obviously will differ if there is some, if there's some left-hand side of the event specification. And so what we need is to store two variants. One which contains the full information, including the step number and or UUID, and one that strips them out.
Yes.
But I haven't done that yet. So all that happens right now is that it just assumes that you don't want any of the additional information when you call one of the graphs.
I think we may need this, because I think in the thing I'm trying to write, I think I need this information, because I think I need to be able to make, I haven't thought it through here, to be able to make a causal graph that, yes, we need to be able to make the uncombined causal graph.
Sure.
In which the different events, that's the critical thing that we don't yet have.
Yep. Okay. In which case, so I'll have to add some functions that remove additional information when it exists. And
I think so, yes.
There are some issues about, we're going to have two different lists of events, and then we're going to make sure that there's a direct correspondence from one to the other, because we're going to use one for doing the computation and then the other one for doing the visualization.
Well, really? I mean, why not? But they're different events. I mean, we won't be able to merge the event. Well, I see. You're saying
when you draw something like a causal graph, right, you want to have the event specification that's specified in the options. But we don't want to have the event specification that's specified in the options when we're actually generating the causal graph.
So, but that event, we get a list of events. Why not take that list of events that we get, and there's just a big bucket of events. It's a big list of events, right? Mm-hmm. Why don't we just have the metadata associated with each event in a corresponding list? And we just look up in the corresponding list. Because every event is unique, right?
Yes. Yep. But not every state.
That's correct.
Right.
Well, I think that I personally recommend some degree of hackery here. so that we don't have to redo the whole innards of everything.
Yeah, right. I just don't know what the elegant way of doing that is, so I haven't done it yet.
Okay, well, can you have a think? And I'll be around in another maybe hour and a half, 2 hours.
Okay.
I can send you mail or call you at that time, and let's see if we can.
Actually, yeah, send me a mail. I can't guarantee I'll be able to. My phone reception is not great.
Okay. All right. Okay. All right. Talk to you soon.
All right. Talk to you in a bit.
Bye.